Hello. In this video, based on Chapter 14.2 in your textbook, I'd like to talk about acid-base theories. And most of this video is going to talk about three theories or models that we use that help us to understand acids and bases and also to understand their properties and reactions. And these theories are, in order, the Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory. And I'll talk about each of these in turn and describe how they help us understand acids and bases and what essentially their definitions of acids and bases are. Let's begin with the Arrhenius acid-base theory. Arrhenius was a Swedish scientist in the late 1800s who studied acids and found one thing in common. He found that all solutions of things that we call acids contain large concentrations of the hydrogen ion, H+, in solution. So, the Arrhenius definition of an acid is a substance that increases the concentration of the hydrogen ion in aqueous solution. So in other words, if I put something in water and it dissolves and I find that I have formed more hydrogen ions, then that substance is called an Arrhenius acid. So let's think about this for a minute. What exactly is the hydrogen ion? Well, we know a hydrogen atom consists of a proton and an electron. Well, if the hydrogen atom has lost its electron, it is nothing more than just a plain proton. Well, that's not going to be very stable in aqueous solution. And in fact, once we form the hydrogen ion in solution, it will immediately react with a water molecule, which we have lots of. It will jump on one of those lone pairs, forming a new covalent bond, and in the process, forming this polyatomic cation called the hydronium ion. So, when we write H plus aqueous, that is synonymous with H3O plus aqueous. And in fact, I am perfectly fine with using either of those to represent the hydrogen ion in solution. H3O plus aqueous is more chemically accurate, but H plus aqueous is a perfectly acceptable abbreviation because every chemist in the world knows that H plus aqueous simply means H3O plus. Okay? So, let's take an example. If I consider the molecular compound hydrogen monochloride, which is a gas as a pure substance, when I dissolve hydrogen chloride gas in water, I form a solution of the hydronium ion and the chloride ion. Okay? That essentially is a more complete and accurate way to represent aqueous hydrochloric acid. Okay? So another way to write this is simply HCl gas forms H plus aqueous plus Cl minus aqueous, another way to represent hydrochloric acid. Okay? So in this case, we would say that hydrogen chloride is an Arrhenius acid because it increases the concentration of the hydronium ion in solution. Now, Arrhenius also studied solutions called bases, and he found that they all contain large concentrations of a different ion, the hydroxide ion, OH-. So the Arrhenius definition of a base is a solute that increases the concentration of the hydroxide ion in aqueous solution. So if I put something in water and it dissolves and I find that I've produced OH-, that means that that substance is an Arrhenius base. Okay? Well, how does it do that? What are the ways in which a compound can form hydroxide in solution? One of the most common is by dissolution and dissociation of a soluble metal hydroxide salt. So for example, sodium hydroxide, according to the solubility rules, should be soluble because it contains the sodium cation, and it is. And when it dissolves, it forms the sodium cation plus the hydroxide anion. And because it forms OH-, we're going to say that sodium hydroxide is an Arrhenius base. Now, we can also form hydroxide by the ionization of a molecular compound like ammonia. When I place ammonia in water, it reacts with water in a kind of interesting way. It does so by removing H plus from the water molecule. It ionizes the water molecule, and when the ammonia gains H plus, it forms the ammonium cation, leaving behind the hydroxide anion. Okay? But once again, in each of these cases, because OH- is one of the products that we get when we put that solute in water, each of these substances is considered an Arrhenius base. Now, I want to make one important point here because I've used different words for these different processes. Dissociation represents the separation of ions in solution that previously existed in an ionic compound. On the other hand, ionization means formation of ions that didn't previously exist, and that almost always happens when a molecular compound reacts with water. So dissociation and ionization both form ions, but they are different processes. Our second category of reactions is called second theory is called the Bronsted-Lowry acid-base theory. Bronsted and Lowry were two scientists who in the early 20th century came up with a more general definition of acids and bases. So according to the Bronsted-Lowry theory, an acid is a molecule or ion that is a proton donor. What does it mean to say that it's a proton donor? It means it gives away H+ in a reaction, whereas a Bronsted-Lowry base is a molecule or ion that is a proton acceptor, which means that it accepts or receives the hydrogen ion in a chemical reaction. So a Bronsted-Lowry acid-base reaction is a reaction in which one of the reactants, the acid, gives away hydrogen ion to another reactant, which is the base, and a synonym for the Bronsted-Lowry acid-base reaction is a proton transfer reaction. Let's take an example. If I react hydrofluoric acid with water, hydrofluoric acid gives away its proton, its H+ to water, forming the hydronium ion and leaving behind the fluoride ion. Okay? So according to the Bronsted-Lowry definition, hydrofluoric acid would be the acid because it's giving away H+. Water would be the base because it is accepting H+. And in the next section of this unit, we will talk about Bronsted-Lowry acid-base reactions in a bit more detail. Now, here's an important thing, and you may have noticed when I chose this example, you may have said, hey, look, H3O+ is being formed. Doesn't that mean that HF would fit the definition of an Arrhenius acid? In fact, it does. Okay? In fact, because all Arrhenius acids donate the hydrogen ion to water to form the hydronium ion, remember we said an Arrhenius acid is a substance that increases the concentration of hydronium ion, then that means that all Arrhenius acids are also Bronsted-Lowry acids, which means that the Bronsted-Lowry definition is a more general definition of acids. Now, notice that the definition of the Bronsted-Lowry acid-base theory does not mention water at all. And in fact, you do not need to have your Bronsted-Lowry acid-base reaction take place in aqueous solution. That's also one of the things that makes it a more general definition. And in class, I will demonstrate a Bronsted-Lowry acid-base reaction that takes place in the gas phase, one of my favorite demonstrations. Now, our final and most general definition is the Lewis acid-base theory or definition. And you'll see that not only does this not involve forming hydronium ion, it doesn't even involve water. Okay? So, according to the Lewis definition, a Lewis acid is a species that accepts a pair of electrons to form a new covalent bond, whereas a Lewis base is a species that donates a pair of electrons to form a new covalent bond. So in a Lewis acid-base reaction, one species, the base, donates or gives away a pair of electrons to form a new covalent bond. Now, I can do a generic representation of this by representing the Lewis base like that, and that blob with two dots in it represents a lone pair, and as you'll see, a Lewis base must contain a lone pair. And over here is my Lewis acid, which has some kind of empty orbital in it, or it is in some other way electron deficient. So the Lewis base gives away its electron pair to the acid, and in the process, a new covalent bond is formed between what used to be the Lewis base and the Lewis acid. And let me give you an example of that. There is a molecular compound called boron trifluoride, and in the gas phase, boron trifluoride reacts with ammonia to form this molecule that I'm not even going to try to name because it's really complicated. But I can draw the Lewis structure, or Lewis structures in general. So here's boron trifluoride, Notice that the boron is electron deficient. It does not have an octet. There's ammonia. Hey, look, it's got a lone pair. So ammonia behaves as the Lewis base because it provides a pair of electrons. It basically attacks the electron deficient boron with that lone pair. And in the process, we form this new molecular compound that has a new boron-nitrogen bond. And I have my 3 hydrogens here. And what you see right there, I'm going to draw over it in yellow, is the new boron-nitrogen covalent bond formed in this Lewis acid-Lewis base reaction. And is water required? Absolutely not. You do not need water for a Lewis acid-Lewis base reaction. Does the hydrogen ion have to be involved? No, nothing in the Lewis acid-Lewis base definition even mentions the hydrogen ion. Okay? So, in order from most specific to most general, the most specific of our acid-base theories is the Arrhenius theory, because it specifically talks about increasing the concentration of hydronium or hydroxide in water. The most general is the Lewis theory, and in between is the Bronsted-Lowry theory. So, let's move on. Before we finish the video, a couple more concepts about acids and bases. This is really important. Acid strength. Okay? Now, the strength of an acid does not refer to the concentration or molarity of the acid. So it is not correct to say that because a particular acid has a very, very high molarity that it is strong. Acid strength means something else. It refers to the extent to which the acid is ionized in aqueous solution. Let's take an example. Hydrochloric acid reacts with water to completely ionize to form the hydronium ion and chloride. And in fact, this ionization occurs 100%. Therefore, we would describe hydrochloric acid as being a strong acid. On the other hand, hydrofluoric acid only partially ionizes in water to form the hydronium ion and the fluoride ion. And in fact, it forms an equilibrium, which we sometimes represent with the 2 arrows pointing forward and backward. So it's an equilibrium process. And depending upon the initial concentration of the hydrofluoric acid, this could only be about 5% ionized, meaning that out of every 100 HF molecules that I put in aqueous solution, only about 5 of them will form the hydronium ion and fluoride, and 95% of them will remain unionized. So because it is only partially ionized, we would describe hydrofluoric acid as a weak acid. So hydrochloric acid is strong because it's 100% ionized in solution. So if I were to ask you the question, which would I consider to be stronger, 1 molar hydrochloric acid or 0.000010 molar hydrochloric acid, you would say neither. You would say both are strong acid solutions because we know hydrochloric acid is fully ionized. So that's kind of a trick question. Okay? On the other hand, hydrofluoric acid is a weak acid because it's only partially ionized in solution. And that doesn't depend upon the concentration. You could have a very dilute solution of hydrofluoric acid or a very concentrated solution of hydrofluoric acid. They would both be considered weak acids. Now, that raises the important question, how can you tell whether it's a strong acid or weak acid? Well, experimentally, it's pretty straightforward. Because acids are always electrolytes, you could measure the electrical conductivity. So a strong acid would be a strong electrolyte, which means that it would conduct an electric current very well, whereas a weak acid would be a very, very weak electrolyte and only conduct an electric current slightly. Or, which will be the case in this class, look it up. I do not in this class expect you to memorize which acids are strong and which are weak, and you are perfectly fine using some reference work to determine whether an acid is strong or weak, if you need to. So what's a strong base? The most common strong bases are metal hydroxide salts, okay? Because a metal hydroxide salt dissolves and dissociates to form the hydroxide anion. And as we said before, sodium hydroxide dissolves in water to form the sodium cation and the hydroxide anion. So that would be considered a strong base. A weak base only partially ionizes in solution to form the hydroxide ion. So ammonia, as we said before, undergoes an ionization process in water to form the ammonium cation and the hydroxide anion. But once again, this is only a partial ionization, as indicated by the back and forward equilibrium arrows. And in fact, depending upon the initial concentration, this only undergoes ionization to about 5% or so. Now, let's think about the ionization of nitric acid. HNO3 is nitric acid, and in water I can write an equation to show it forming the hydronium ion and the nitrate ion. So obviously one of the things I expect you to be able to do is to write an equation to represent the ionization of an acid in solution. Okay? Now, because nitric acid, which has the formula HNO3, only has one hydrogen ion that it can donate to water, we call it a monoprotic acid. Monoprotic simply means one hydrogen. But now let's consider sulfuric acid, which has the formula H2SO4. Well, I can write a similar equation to represent the ionization of sulfuric acid to form the hydronium cation and the hydrogen sulfate anion. But look, the product of ionization, that is HSO4 minus the hydrogen sulfate anion, has another hydrogen ion that it can donate in a second and subsequent ionization process. HSO4 minus reacts with liquid water to form another hydronium ion, and now the sulfate ion. Okay? Well, when an acid has more than one hydrogen ion to donate, we call it a polyprotic acid, because poly obviously means multiple or more than one. If it has two hydrogen ions to donate, like sulfuric acid does, we would specifically call it a diprotic acid. If it has three hydrogens, it would be called a triprotic acid. And yes, for the curious, there are such things as tetraprotic and pentaprotic acids, but they're not very common, and we're not really going to deal with them this year. Okay? Now, the important point is that in a polyprotic acid, the product of the first ionization still has one more hydrogen ion that it can give away, and that these ionizations are successive, which means they don't happen all at once. They happen one after the other. So what I expect you to be able to do is the following. If I give you the formula of a polyprotic acid, you should be able to write balanced equations to represent each of the successive ionizations of that particular acid. And you can always use that as your model for showing these ionizations. And I believe that's all I want to say about acid-base theories. In our next section, we will talk about acid-base reactions.